Arturo Ordonez from Solar. He can't be here in person today. He's in Spain. He couldn't make it. I have a recording which I'm going to play. It's 4 minutes 30 seconds, and then we will get him live on the phone to answer a question from the judges.
This study addresses the optimized design of a three-bedroom detached house located in El Pallaresos, in Catalonia, Spain. This study addresses the optimized design of a three-bedroom detached house located in El Pallaresos, in Catalonia, Spain. Our main goals were to accomplish high energy efficiency, reduce the ecological footprint, and low construction cost. All of this using materials that are healthy for occupants. We implemented three important approaches: to apply a simulation-driven design from the very beginning, to evaluate many possible design solutions, and to consider consistently the environmental and economic performance. The project involved three main phases: an optimization analysis based on a genetic algorithm, the development of the architectural design, and a parametric analysis to fine-tune the project. The optimization analysis allowed us to investigate efficiently the performance of many possible design solutions. We use a method that involves coupling a simulation engine to a genetic algorithm, both provided by the main software employed. The analysis was driven by two objectives: to reduce the carbon emissions associated with energy consumption and to minimize the initial construction cost. The optimization analysis included 7 design variables, each with a number of options, 7 building forms, all with the same main spaces and the same usable floor area. The 3D models included the internal distribution of common dwelling spaces, 11 window-to-wall radius for the main spaces of the house, 46 construction sets, mainly defined by the combination of 2 design variables, thermal mass and insulation. They are also divided into 2 groups, one with common Spanish materials, another with components of cellular concrete, 12 glazing options which result from combining 2 design variables, the number of glazed panes and the glazing type, and finally 4 shading options for the windows on the main spaces. The optimization search space was of around 170,000 solutions. The genetic algorithm allowed us to find the optimal solutions, simulating only about 7,000. The graph shows the full results of the optimization runs, identifying each form option with a color. The x-axis indicates the operational carbon emissions, while the y-axis indicates the initial building cost. This graph shows only the Pareto forms of the 7 forms. It's evident that the first 2 offer the best performance. Finally, this graph shows only the Pareto front of the first form, considered the overall best one. It also highlights 3 preferred solutions. From the optimization results, in this phase, we developed the architectural design project, further considering the specific requirements of the owners. We adopted a solution that could be defined as intermediate, since it combines the 2 most optimal forms. Instead of window shading devices, the project included more architectural self-shading, in order to reduce the cost. In the third phase, we carried out a series of parametric simulations, aimed to verify the performance of the project and further optimize constructions and glazing. It was based on a simulation model derived from the architectural design project. In total, we simulated 12 solutions, which derive from the matrix of options shown in this figure. In this case, to evaluate the design solutions, we extended the performance scope to consider the global carbon emissions and the global cost. The graph shows the global cost with the blue line and the global carbon emissions with the red one. The global cost tends to increase gradually as the constructions are improved, while the solution based only on cellular concrete clearly produces lower global emissions. The solution pointed out by the blue arrow has the lowest global emissions and an affordable global cost. We finally selected this solution for the project. 3 additional models were simulated to contextualize the results of this study. The results show that our project offers saving of more than 17,000 euros compared to the common project, and more than 32,000 euros compared to the previous one. Also, we have a reduction of more than 42 tons of carbon compared to the common project, and more than 60 tons compared to the previous one. This project demonstrates the benefit of implementing a simulation-driven design process, especially if optimization analyses are executed from the very early design stages. Thank you very much for your attention.
Can you hear Arturo? Yes, great. Great presentation, video. Can you just introduce yourself and then the judges will ask you one question.
Okay, thank you very much. First of all, obviously for talking about my name is Arturo Ordonez from Solar, a small company of architectural design and energy analysis in Mexico and Spain.
Great, thank you Arturo. One question please, I'll repeat it for Arturo.
Okay, thank you very much Arturo. I see with the optimization you focused on carbon emissions, environmental parameters and cost parameters. Can you see yourself repeating optimization for domestic buildings using other optimization parameters for health and well-being as well?
Great question. Arturo, did you hear that?
Yes.
Okay, great. So the question was, can you see yourself using optimization in domestic buildings, especially considering health and well-being parameters?
That's part of the research, most especially about the selection of Daines, yeah? Because the owners, they were very worried about this issue. So we did an investigation about different matters, for example, the wood, and finally, we found that, for example, the cellular concrete is a very nice material in this aspect because they don't have this kind of contamination and this is very healthy for us.
Okay, Arturo, thank you very much.
Thank you very much.
Thank you, bye.